Welcome to the Flight Instruments lesson. You may note that alternate terms for flight instruments include Electronic Flight Information Systems, EFIS, or Electronic Information Systems, or EIS. In this lesson, we're going to go through a few points, including why is this important? How does the flight instruments lesson relate to other systems? Review of a notable accident, talk about some system overview concepts, talk about abnormal operation, and then a few review questions. Why do we need to know about flight instruments? As aviators, we need to continually rely on our instruments for airspeed, altitude, attitude, heading, vertical speed, navigation, approach minimums, and other data. This information comes from many sources, and a lot of those sources have an alternative or more than one alternative. We need to be able to understand in the event that those displayed information become unavailable, or a sensor fails, or a data concentrator unit fails, how do we redisplay or get access to critical information to ensure safety of flight? So how are flight instruments or EFIS related to other systems? Sensors that provide information to our EFIS displays may also provide information to other systems. Examples of those include automatic flight or auto flight, navigation, cabin pressurization, electrical system. We actually receive power, obviously, for our probes, our display, our data concentrators. All of those elements come from our electrical system, so we depend on that. Warning systems such as GPWIS, to be discussed in a later lesson, as well as other elements. TCAS need information from our flight instrumentation. We also receive information for ice protection system. And then obviously our aircraft which are installed with a warning system, for example, ICAS, which is in a later lesson, or ECAM, which is on Airbus aircraft. So I'd like to take a moment now to discuss a notable incident, which flight instrumentation was a key element. That accident is Air France 447. Air France 447 was a tragic incident which occurred in June of 2009. There was an Airbus A330 which was flying from Rio de Janeiro to Charles de Gaulle Airport in Paris. Fairly soon into the flight, the crew encountered thunderstorms while out over the Atlantic. They entered a condition which caused severe icing, and the probes were iced over despite being heated. Those probes, those pitot probes, were iced over during an encounter with severe icing. And due to multiple probe failures, this caused confusing indications to the crew as well as confusing indications to the FMS, the Flight Management System, and Autoflight. And basically due to being in thunderstorms at night over the ocean, little reference which could be relied upon, the crew ended up mishandling the error and basically stalled the aircraft from over 30,000 feet and then ultimately impacted the ocean. And actually that aircraft was not found for nearly 2 years as far as determining the probable cause. So a very tragic incident, but one of the contributing factors, although there were many, the crew was receiving confusing indications in the flight deck on their instrumentation because of multiple probe failures in severe icing. So there's much more detail related to that incident and accident, and certainly encourage you to do your own research and look into that with greater detail. All right, so now let's talk about some concepts related to flight instrumentation. As I mentioned earlier, electronic flight information systems, or EFIS, and the term EIS, electronic information systems, can more or less be thought of synonymously. To show an example of this, on the lower left-hand side of the screen, you're going to see a CRJ-200 flight deck display, and this comes from smartcockpit.com. It's very small, but you can see on the outside of the display, that would be a PFD. The inner display just to the left would be an MFD. The center two displays, sort of where that 19 is labeled, the left of that would be called ED1 or ICAS display 1. The right one would be ICAS display 2. The two screens that are sort of below the number 16 and 19, the outboard screen would be a PFD, or a primary flight display, and the inboard one would be an MFD, multifunction display. So you sort of combine those, would be sort of, or I guess technically the outer two, the PFD and MFD, would be the EFIS, and then the two in the center would be the ICAS displays. If we look at an example of an Airbus, we have the similar example. We have a PFD on the outboard side, and this is in the graphic on the right side part of the screen. So those we have PFD1 on the captain's side, PFD2 on the FO's side. And then inboard of that is your nav display, and this is actually a similar arrangement and name as we see in the 737. The nav displays are inboard of the PFDs. And then in the center of display, we have our ECAM displays. You have an upper ECAM and a lower ECAM. The upper ECAM is called the engine warning display. That's where engine gauges are. That's where our failure messages will show up. We have our flap indications, and some other information will show up on that. And then our lower systems display is where our variety of systems pages of hydraulics or anti-ice or air conditioning or whatever it might be would show up on that page. So again, this is just a summary of we talk about EFIS, and I introduced, I know, another related topic to this, which is the electronic information system, and addition of sort of the ICAS or ECAM displays as well. So what's critical to EFIS is understanding the fact that we've got data coming from a lot of different sources. And dissimilar to small general aviation training aircraft, there are multiple pitot-static, and there's some additional probes on these aircraft, or air data probes, which are not on small GA aircraft, including angle of attack or TAT probes, as well as ice detectors. So it's important to know that depending on the aircraft, there are a lot of different combinations of these you may see. It's fairly common to see 3 pitot probes, generally 1 pitot probe for captain's instruments, 1 pitot probe for first officer's instruments, and then usually a standby. That's a fairly common arrangement. Sometimes these pitot probes are also a combined pitot and static probes, so they'll actually in the same probe have both pitot and static information. And then in some cases they're entirely separate, so those static sources and those pitot sources are kept on separate probes or locations. We also commonly will see 2 AOA vanes, or alpha vanes, depending on your aircraft. They'll call them different things, but this is of course helping us determine the angle of attack of the aircraft, similar to sort of the shape of a feather on the back of an arrow, and it's sort of aligning itself with the relative wind. We also have TAT probes, and we'll talk a little bit more about total air temperature later and what exactly TAT is. Commonly there's at least 1, and if not 2 on the aircraft. Ice detectors, there are a variety of different ice detectors. Some of them are sort of a passive system, meaning it's just a piece of metal that's sort of mounted in a visible place for the flight crew to see when structural ice is accumulating. And then in some case they're more advanced, and they'll actually use more, they'll use a sort of a vibration which determines, if there's ice accretion which is occurring, the vibration frequency will change and then signal an alert that ice is accumulating on the aircraft. And that actually does occur on the CRJ aircraft. So that's something we'll see in later content. So there's a variety of different sources and probes, and there's oftentimes redundant probes on the aircraft. So how do we get information from our sensors or our air data probes to the displays? And I just have a simple diagram here. I think it's important to keep simple sometimes. The sensor outside the aircraft ultimately is going to feed information generally to some form of a data concentrator or a switch or a data bus. Sometimes we have air data computers which convert an analog to a digital signal. And then actually sometimes there's more than one data concentrator or switch or data bus. So it might actually flow through multiple sort of intermediary stops before eventually getting to the display for the crew. So when we're thinking about, when we have malfunctions occurring, a malfunction can occur at any one point in this process. The sensor could fail, or the data concentrator or data bus could fail, or the display could fail. So when we're talking about how we interface with our EFIS system, you have to understand that any one point in these things can fail, and then you have to figure out how to fix it, how to remediate it. One item I noted on the bottom of the screen there is standby instruments, sort of by their nature, try to bypass some of these routing of data or complicated routing that we have. And so the idea there is if we have multiple failures and things are not going well that day, theoretically your standby instruments are going to be unaffected and still available to you. So more information will become in your specific lessons. As I noted earlier, I just wanted to show you a slightly different diagram. We have a lot of different data sources on the aircraft, and those data sources ultimately are shown on a display. Those data sources, if they're working normally, of course life is good, and that's going to be 99% of the time. For that 1% of the time, you have to understand that if there's a failure of a data source, whether it's the air data probe itself, or whether it's a module, a data concentrator module or unit, that we have to figure out how to redisplay the information. So sometimes that switch occurs seamlessly to the crew, so sort of automatic reversionary modes, if you want to think about it that way. And then in some cases, the crew has to take action, and we'll talk more about that later. But you see in the sort of the right-hand side of the screen, data concentrator 2 might have ability to pull data of the same probe, for example, a pitot probe. It could pull information from pitot probe 1, but it also could pull information from a standby pitot probe. And so if pitot probe 1 fails, we can still pull information and redisplay it elsewhere. So it's important to think about the system architecture as a crew, and then how do I get the information back in the event that it fails. And then the biggest thing is just understanding, is this, in the event of a failure, does automatic switching occur, or do I have to manually select data if a backup exists? So that understanding how that data flows is important. Another topic that is on more recent aircraft, I would say when I say more recent, even the last 30 years, or probably even a little bit more than that, there's this idea of the dark cockpit or the lights out philosophy. And so the idea here is when you're looking at your displays, or if you're looking in and around the aircraft and how we receive information, one of the thoughts is, well, if you don't need the information, or if it's in an automatic mode, or if it's working normally, let's sort of keep the light extinguished. If there is some sort of abnormality, then illuminate it to the crew. So that would be, in the event of a fault, or if you have a system which is it only works during part of the time, for example, ground operations, or if it's an icing system which is not typically used all the time, maybe then illuminate a light. And so the same, this is sort of even more broad than EFIS, but EFIS, the EFIS system sort of adheres to this generally as well. And it is a human factors and workload consideration. And the idea is, if in the event that something is occurring which is outside of the routine, you can quickly identify by looking, even just in your peripheral vision, where in fact this system is either faulting or it's outside, operating outside of the routine, that sort of idea. Here's an example of both the EFIS displays and sort of the image is actually from a simulator on both images, but you can see where that dark cockpit or the lights out philosophy is fairly important. In the event you are in fact flying in at night or low light conditions, you don't actually want to have all sorts of stimulus in front of you, because you need to be also transitioning to the visual environment and ultimately landing an aircraft, for example. And so you could see that in the event of an abnormality occurring, it's pretty easy to identify. There would be a light illuminating, and it's very easy to see. And also the master warning or master caution lights would illuminate. And so to that end, that's actually a part of the next lesson, but I wanted to sort of show you an example of a dark cockpit or lights out philosophy. Also note that the overhead panel, which on most aircraft contains a lot of the core systems interface, whether it's generators or bus ties or hydraulic switches or shut-off valves or whatever it might be, that's often on the overhead panel. And so this lights out philosophy also is very noticeable on the overhead panel. And then when something occurs, it's very easy to identify, as a light would then illuminate. Oh, well, very briefly, I wanted to talk about color logic. And one of the ideas of the color logic on our screens is that when we move from aircraft to aircraft, there should be some semblance of sort of intuitive transfer of how do we process this information coming from our displays. And so there's actually a guideline. FAA Advisory Circular 25-11 has this information. And if you go from an Airbus to a Boeing to a Bombardier airframe, the displays are certainly not the same, but their orientation is generally similar or pretty much the same as far as, where is airspeed, where is altitude, where can I find vertical speed, how do I interpret my attitude information. That's all pretty easy to interpret, including colors, right? So we all associate green with being normal conditions or engaged modes. That's a pretty common sort of theme. Red we know as being warnings or abnormal or limits of flight envelope, exceedances, that sort of thing. So this is not all by chance. We as aviators want to be able to fairly easily interpret different conditions. I do want to caution you, though, that from airframe to airframe, for example, a PFD or an ND MFD do have differences that you will have to get used to, and there are some of them are fairly significant as far as how you're going to receive information or what symbols are important, and some of them are fairly minor. And so as you go through initial qualification from one aircraft and then maybe qualify on another aircraft, that's something that you will have to adjust to, as some of more nuanced differences between the displays. Here's just another example of different color logic, which is used in different aircraft. So yeah, if you want to see more information, the FAA Advisory Circular 25-11 is where you can find that. Wanted to mention, we talk about data flow, and in your lessons you're going to learn more about this, but you have to know failures do occur. And the failure, as we saw in the previous diagram, could occur in a sensor, a data concentrator, a screen itself can fail, or even your power source. And you, the crew, have to be prepared and are usually going to be trained on this in your initial qualification and often in recurrent training or CQ as well. And so, you know, you'll fly by reference standby instruments if needed, if the conditions require, and then of course redisplay the data source. So that could be, you know, switching to a new display if automatic switching didn't occur, or using a reversionary panel. And unfortunately, I show an example on the right side of the screen is United 266. This was an aircraft which was departing, I believe it was a 727, departing LAX and going to ultimately Milwaukee with an intermediate stop at Denver Stapleton, I believe. And the aircraft had multiple generator failures. I'm oversimplifying a bit, but ultimately they lost all sight in the flight deck, and they lost ability to determine up from down. So the quote from the NTSB is, the board determines that the probable cause of this accident was the loss of attitude orientation during a night instrument departure in which the attitude instruments were disabled by a loss of electrical power. So now aircraft have more reliable backup and standby power, as well as standby instrumentation are often required to have an alternate source so that this sort of accident doesn't occur again. So I do encourage you, for more reviewing, you're welcome to review United 266. And a few operational review questions. We see, and this is a review from earlier, how does information get from the sensors to the screens? In your individual lesson, I really encourage you to pay attention to this. Look at the diagrams and look at, you know, pay attention to where the crews are going to interface and when they need to interface. If a sensor is providing good information and that data concentrator or the display electronics unit or the data concentrator unit or whatever the name for that is giving good information to a good display, life is easy. All right, and then if something happens, then we need to get involved. So if that data flow is interrupted, we need to use those reversionary panels. Some cases the action occurs automatically and some manually, and I'll review one here in a moment. If all or most screens are affected by a data flow failure, you got to fly by reference to standby instruments and then work through the problem with your crew member using good CRM and, of course, your company handbooks and manuals. So here's an example of a very specific one. Let's say you lose pitot information on the captain's side. There should be information. For one, the good news is if it's just the captain's side, the FO is still going to have access to airspeed information, so that's good. Using the reversionary panels, this would be an example where the crew would likely have to intervene and redisplay good information on the captain's side using a switching panel or a reversionary panel. So that would be a fairly, losing one air data source on pitot source if you have two others. Yeah, it's important, but if you've got two others that are working fine, this flight should be able to be completed without any incident. And then of course you're going to contact maintenance through ACARS or other available means and then have it addressed on the ground. So there should be a way to remediate this with fairly low impact to the crew. If you have more than one failure of a redundant system, then it gets a lot more complicated, obviously. So here's a good one. If you have an entire PFD screen that fails, this would be a little bit more noticeable, particularly if it occurs during a critical phase of flight, such as takeoff and climb, or approach and landing, and then it becomes even more dangerous if it occurs in weather or if there's terrain in the area. You know, those are certainly factors. Now, if you have a single PFD failure, when you have two, the easy answer is if that person was flying the aircraft, you know, sort of up to the captain. But if need be, you know, the other crew member can take over if necessary. However, I want to mention that on certain aircraft, for example, the A320 and 737, if a primary flight display fails, it will automatically switch over to the nav display. On a CRJ, if a PFD fails, the crew has to use the display reversionary panel to fix that. So it's important to know from aircraft to aircraft that switching logic or the reversionary logic does differ. It also differs from screen to screen. So one logic or one screen failure which will cause an automatic switch may not cause automatic switching in another set of screens. So it's important to understand the difference. Another topic I wanted to talk about, because it's not common in small GA world, because we're not typically going 300 knots or 0.8 Mach in a Cessna. Pretty uncommon. Is this idea of static air temperature and total air temperature. So this definition I thought was it's concise, or fairly concise. It's from flyingmag.com. TAT, which is total air temperature, and that's one or more probes that we have installed on transport category aircraft. Total air temperature is SAT plus the temperature rise associated with high-speed flight. All right, and so that temperature increase is called ram rise, result of heating of the air due to compression. And so effectively, you know, you have to understand that SAT and TAT may be used during as a part of limitations, for example. There may be fuel temperature limitations where TAT may be used, or during use of icing, ice protection, whether it's cowl anti-ice or wing anti-ice. They may be using you know, TAT or SAT in your company manuals to determine whether to use you know, use anti-icing protection. So there's this probe. It's not on small GA training aircraft, but it is on you know, faster, higher performance aircraft, and so you have to sort of understand, okay, what is total air temperature? How is it related to static air temperature? And what do I do with that? So I wanted to sort of offer that, because I often see where there's some explanation is needed on this topic. I do encourage you for additional review of why flight instrumentation and why we need standby instrumentation and good lighting in the flight deck is the case of United 266, as I talked about earlier. So go ahead and do some search for that, do your own research. It is an interesting, unfortunately tragic example, but we have learned from that and we design aircraft better now than we used to. If you want to see more information about how flight instrumentation in aircraft should be designed or oriented, or how you know, the pilots should be able to interface with the EFIS system, Advisory Circular AC 25-11 has very detailed information. At this point in time, go ahead and review your ethos module. And if you have any questions, you know how to get a hold of me. Hopefully you've enjoyed the flight instruments lesson.